G'day. This is part 3 in my series on automating my garden. It's using MicroPython on a microcontroller. At the moment I'm growing the seedlings that I'll be transplanting to my garden. Here they are, and there's the garden in the background. I'll probably do that in about 3 or 4 weeks at the end of April. For this video I'm going to look to flesh out how I'll use a Raspberry Pi Pico W microcontroller to host web services that I'll use to monitor and control my garden. At the same time, I also want to have a background task running at the same time to run automation functions. This is the first time I've tried to perform this level of multitasking on a microcontroller. Normally I'd use something like a full-blown Raspberry Pi to do this sort of thing, kind of like what I did on the Solar Shed project. I'll probably end up putting most of this stuff together, put it in a waterproof case, and put the components in as part of getting the Garden Pico project going. So all that will happen in this video as well. Once all this is working, I'll look to return to the Angular application that I use as the front end to the Garden Pico web services. So I'm planning to cover the Angular and the irrigation hardware in the next video. That'll be part 4. The final video, part 5, probably a couple of months later, I'll look to tie everything up, look at any loose ends I've got, how I've waterproof things, and see how the irrigation in the garden's going.
So first I wanted to check that I could do what I wanted with micro asyncio function in MicroPython. So it allows multiple concurrent tasks to run. So basically I want to be able to run time-based automation. So we can see here under the main event loop of asyncio IO that there's going to be some time-based automations. So basically I want this routine to wake up every minute or so, check whether the hours passed, in which case it logs all my monitoring information to a file. Also I want it when it to wake up to check things like for the irrigation control, whether the monitors tell me I should do an automatic irrigation or not. If the irrigator's already on, check how wet things are, or if it's running manually, check how long it should run until it turns off based on a preset default value for that. Same for webcam. If I've turned it on, I want it to turn off automatically after a preset time so I don't waste battery. So those are time-based automations. But at the same time as those things are going off or waking up and checking for things, I also want the MicroDot web server running all the time, and that's what we've already seen. It's going to provide capabilities for things like the web services. So we saw that in the last video where it's turning a relay on and off based on a web service, and also be able to serve up the Angular application. So I know MicroDot didn't do that, but I just want to make sure it can run concurrently with the timer-based functions. So to set a test up, I just added a LED to my microcontroller at the moment. So what I'm going to try doing is have that LED periodically wake up, turn on and off, same time as MicroDot's running, and we'll see whether the whole thing's going to work. So the changes I made to my code for this test is I added a LED and have that on pin 4. Turn the LED off to start with. I've added this blink routine, which is a coroutine in SyncIO's parlance, and it's basically going to always run. It'll turn the LED on. It'll give control back to SyncIO for these waits and sleeps. So sleeps for a second, then turns the LED off, sleeps for a second, and just stays in that loop forever. So that's my background coroutine that I want to have running the same time as all the normal MicroDot stuff's running. So the way I got this to run was I added this line in, SyncIO create task blink. So that's going to fire it up, have it run in the background. And then I'll pass control onto the next line in my code here, where it runs the MicroDot application. And remember, MicroDot's running this version, the MicroDot asyncio version, and the asyncio version of MicroDot, as we see here, will run it as a synchronous operation, so it'll return control to syncio periodically as well, so allows that other background task to get a look in. So let's see if this is going to work. Okay, let's check asynchronous stuff's going to work. So I've got Visual Studio Code on the left hand side and a web browser on the right hand side, and we can see my microcontroller set up with the LED. It's not blinking yet, so let's fire up the program. Okay, so I've got a blinking LED now, so that part of the synchronous routine's going. And let's try calling up garden.home website. And it looks like it's getting the requests and it's rendered the result. So it looks like all the asynchronous stuff's working okay. So next thing I want to do is get readings off my soil moisture meter. So in this diagram it just shows you how I've wired up my meter. This isn't the actual soil moisture meter I used, but it's very close, but I'm using a capacitive one. So I connect up the positive to 3.3 volts, negative to my ground, and then the signal I connected up to pin 36 on the microprocessor. Now if we have a look at the code, if I go up to main, I create a new library called sensor, so I've imported sensor. I'm going to add more code into sensor, and then I'm just doing a sensor read in the main to test this out. Now if we look at our sensor library, what I'm doing is I'm bringing in machine and the pin and ADC functions. I also use time just to be able to get some timing. So I'm setting up the pin here. I'm using pin 36, which I set up as a input pin. And then for the ADC, for getting the voltage off that sensor, I set up an ADC object using that pin number as the actual pin. The other thing I had to do is set the attenuation on the ADC. Otherwise I don't get the full range of voltages out of the sensor from dryness to 100% wetness. So setting the attenuator, I can actually receive all those different voltages and then do something with it. I've already run this, so I already know what values I get back for total wetness and total dryness. So I've set those up those values already. Now for my test code, I just set up a loop, so I run through this 10 times and I'm getting a wetness value between 0 and 10, just as integers, because I don't need that much accuracy or sensitivity. As long as generally I know where the wetness is, it'll work. So that's the formula I'm using to work out a value for those numbers between 0 and 10. Then I do a print of the number, the value that's actually coming in through the ADC, and then my calculated wetness value. Okay, we can see my test environment. So this is my microcontroller. I've connected up the moisture meter. You see it's a little different from the one I showed in the diagram. And I've got a cup of water to measure 100% humidity. And I got a little napkin to wipe off the moisture meter to get it back down to 0. I think we should be ready to go. Let's do a Control D. Okay, it's getting results. And there we should see the range of values. So let's see what we got. So out of the water, I was getting zeros. When I put it in the water, I got 100% humidity. So it went up to 10 because this measures in a range 0 to 10. Then as I started bringing it out of the water, it dropped to 9. I think when I was wiping it down with the napkin, we're getting to the 4s and the 5s, so about halfway wet. And then back to 0 when it was dry again. So I want to provide some protection for the exposed electronic components on the top of the moisture meters. So I printed up this header to shield them all, and also wrapped it with some heat shrink tubing. Should keep the water out. Some other changes. I changed back to the Raspberry Pi Pico W, just I like the form factor better. I've added a voltage divider to be able to measure the battery voltage using the onboard ADCs. And I also added an I2C based temp and humidity sensor, uses the BME 280. Okay, I was starting to feel confident that everything I'd put together is going to work, so I moved everything onto a protoboard in preparation for mounting it up and getting it out in the garden. You can see it here. I think just about everything either screws together or clips together, so it's easy to take this out if I need to do some work on it. So I've mounted all the components on a aluminum board. They'll be fitted to the battery box where I'm going to keep everything in. This connector down here, this is for the 12 volts, so it has 12 volts coming in from the solar controller. That goes to the two relays to be switched either to the pump or the camera. And I also have a sensor line, this green line, going up here that goes to a voltage divider that goes into the ADC on the Pi Pico. The voltage divider is needed to reduce the voltage that's coming from the batteries to a level that the Pico can measure. I have a BME 280, and this is an I2C temperature and humidity sensor. These two connectors here come in from the soil moisture meters, and this connection here is going to be connected up to the rain barrel to 3 switches to be able to measure the water level in the rain barrel. Looking how I put together the whole thing, the battery, the charger and the controller case. So I'm just using a plain old 12 volt battery case, and then inside that I actually put in my 7 VA battery. There you can see the mounted Raspberry Pi Pico, my solar controller, all wired up together. I just need to clip the battery on. That's my battery. So that's most of the hardware I'll go over in this video. I still need to seal up the box, put some waterproof silicone around the screws and things like that to make sure that nothing gets in. Actually put some more screws for the chassis and things to make sure they're mounted firmly. But that gave me a good idea and feeling that everything's going to go together, at least from the electronics side. Probably the next video too will be more on the irrigation as well, setting up the pumps, making sure the right amount of water is getting to the soil, and start making sure everything works together. So the rest of this video I'm just going to have a look at the Raspberry Pi Pico Micropython code. I'm just going to go around the main area. It's not going to be a tutorial on coding for MicroPython, but just look at the main areas, how I set it up. This is the bit I really liked about it, was being able to get a web server running on a Raspberry Pi Pico. It's kind of the next size down from just a straight Raspberry Pi, and still seems to run a web server well, exposes web services and things like that. So let's have a look at the Garden Pico code. So again in main, so I've filled a lot of this in since the beginning of this video. So in main, I'm calling the create task clockWatcher, so that gets it running asynchronously in the background, and we'll have a look at that. But that's kind of all the timing type functions happening in the background. And then just like before, we fire up the MicroDot app to run as well, so that they'll be receiving all the basic web service requests. So let's have a look at that background task first, this clockWatcher. So this goes into a loop in the background, so while true, and then it's sleeping every 60 seconds, so waking up every 60 seconds. It's doing things like if the pump is on, then it adds 60 to the total in the pump in the sensor library. So 1 minute's passed, so we add another 60 seconds to the total duration that the pump's been on, and this is all for collecting statistics on how long the pump's on. Same thing for the cam, but the camera is measured in minutes, so we add 1 to the total time that the camera's been on. We call these 2 routines under relay. Check whether anything needs to be turned off, and there's rules about why things get turned off, such as the default duration that the pump can run. So it only runs for, say, 10 minutes before it turns itself off, because we don't want to overwater thing. Same thing, we've got some rules about when to turn things on. So things like if the moisture level in the soil's getting too low, then it'll automatically turn on the pump. If it's a certain time of day and we've set some triggers for when we should start up the pump, it'll turn it on as well. In this piece of code here, we're just looking at the current time and comparing it with the past, the previous time. If the hour has changed, then we write a log entry. So pick up sensor data, find out how long the pumps and cameras have been running, and write that all out as sensor data. We'll have a look at that. And I also check once an hour to whether I need to turn on the pump based on the moisture in the soil, and I only do that once an hour because I don't want to keep turning it on if there's a delay between watering and the moisture sensor registering the amount of watering that's been going on. And like I said, then it just sleeps for 60 seconds. So interesting one in this this condition that happens every hour is the write log, and what that does is write out to a CSV file. So each day I'll make a new CSV file. So basically it's the year, month, day.csv for that day's entries. Should have an entry for every hour. So this is just what came out while I was testing. So I may not have a full day's worth. So it's got the actual timestamp as a GMT epoch time here. The first 2 numbers are what the current moisture sensor readings are from moisture sensor 1 and 2. It's what the current voltage is on the battery. So all these are dummy numbers while I'm testing this. What the temperature from the I2C sensor is reading, what the humidity is reading from that I2C sensor. The next 2 numbers are the number of seconds that the pump has been on, and then the number of minutes that the camera has been on. And then the first number, last number in this in these logs is the number 1 to 4, depending on what the water level in the barrel is, and that's another condition on the pump, that if the water level gets too low, which would be a 1, then the pump doesn't run. It doesn't try and run the water barrel totally dry. So the next part of this code in main is really all the web services. So we've already seen the web service that's used to turn the pump on and off, and it uses these decorators at the beginning of each service to identify the routing pattern that's used and whether a parameter is passed or not. So let's have a look at these. Let's have a look at sensors as an example. So this one here gets all the current sensor readings. So in the browser, so this is our static Angular website. I haven't updated that yet. That'll be a large part of what's in the next video. But let's try some of these web services. So sensors, one of the options. So this just gets all the sensor data. So again, what my soil moisture meter 1 and 2 is showing. What the battery level's at. Again, I haven't got it plugged into a battery, so that's not going to show 12 volts or anything. The current water level, and then I added these 2 sort of 3 system variables as well. So the amount of memory is free, so I just wanted to keep an eye on memory usage. Garbage collection goes on, so you'll see this vary quite a bit. So as it gets very low, then garbage collection will click in and reclaim most of the memory. I haven't been seeing any problems with that. And then the amount of file space that's left. So this is the total file space that's available on the Pi Pico before I did anything. So close to 800k. But at the moment I've only got 184k free. And I'll probably need more than that for the logs. And you saw that earlier on I was sort of jumping between using an ESP30 and a Pi Pico. I think I'm going to have enough room. So one of the options I have is to use gzip on the static files to reduce their size. So I think once I do that and serve them up as compressed gzip files, then there's going to be a lot more space available, and for my calculation it's going to be plenty to sort of hold a year's worth of garden data in there. Some of the other web services is the history web service. So I can either just say history or give me 24 hours worth of data there about the history data. And this all comes back as JSON data, and that's going to be used in the Angular application. This is very close to what I did with the Solar Shared project. I used a lot of the code, so not too many surprises here. I won't go into the details, but Solar Shared should have more details about how I did that. But the good thing is, because I'm using MicroPython, Python code goes across pretty easily. History has the option of putting a start time as well. So let's just start from this one. If I don't want to get as much data, we can even reduce that more. So I only get a few hours worth of data, and this all will be coming from the Angular application to choose how much data I want. And the other thing is, if I choose more than a 7-day range here, then it'll summarize daily what the totals are for each day, or the averages are, depending on what the metric is. And all of that was very much like what I was doing in the Solar Shared. So we can see the history routing there. The other thing is under the settings, web services, I have settings for the default values for things. So like I said, I can have the pump only stay on for a certain number of seconds, camera stay on for a certain number of minutes, and a lot of that's to do with either conserving the battery used to run the pump and the camera, or to conserve the water usage. So having these default settings is useful. So there's a whole bunch of default settings, including the times that the pump should come on automatically. So you can see all the web services there. So if we go back to our browser and instead look at settings, I can retrieve all the settings that are there. So this is so if I just want to look at one setting, I can say look at pump on seconds, which is set for 120 seconds, and I can also update that. Let's just make it 240 seconds instead. And now if we look at settings, we now see pump on seconds set to 240. So that's mostly how the Angular application is going to be talking to the Pi Pico while it's sitting out there in the garden. And like I said, so most of the next video is going to be about the irrigation hardware, and then updating the Angular client to make use of all these services, and hopefully be almost complete at that point. And then probably the following video will wrap things up and look at how it all looks when it's connected up and sitting in the garden.